Hello and welcome back, everybody. In this lecture, we're going to talk about the heat of formation and calculating heats of reaction. Whenever I say heat, I really mean enthalpy, but we use capital H in the formula, so that's why I like to say heat. So the heat of formation is given this strange little symbol with the triangle, the little circle up there, and the F. So the triangle means change. The capital H again means enthalpy, technically speaking. The subscript F means formation. We'll talk about this. And the little zero there means standard state. So standard state is the commonly agreed upon reference point for thermodynamic values. In chemistry, the atmospheric pressure is used as the reference pressure when we're talking about gases, all right? And when we're talking about dissolved substances in a homogeneous solution, we're talking about 1 molar concentration. Now, there's no official designated temperature reference, but most everybody seems to use 25 degrees Celsius, and that's what the OpenStax chemistry textbook does, and that's what I do. And many thermodynamic tables online are at 25 degrees Celsius. So this is what I'm defining as standard state here, okay? Now, the standard enthalpy of formation, it's a mouthful to even say that, is basically just the amount of heat, right, or enthalpy it takes to create 1 mole of a substance. And we're making that 1 mole of a substance from elements. So for example, if we're talking about carbon dioxide and we want to know, hey, what is the enthalpy of formation for carbon dioxide? We could do a reaction. We could take carbon, we take oxygen, we could combust them, and we could form CO2 and measure the amount of heat given off and find that it's, excuse me, we could find that it's 393.5 kilojoules released, okay? And so we could therefore say the heat of formation for carbon dioxide is negative 393.5 kilojoules. And scientists have done all of these experiments, all of these calculations, and then they've used Hess's law to calculate all the other ones that it would be impossible to calculate for, okay? So the enthalpy of formation does not apply to elements. It only applies to compounds that you're forming a compound from elements. If we have an element is already an element, there's no reaction to create it, okay? So when you look up the heat of formation for chlorine gas or hydrogen gas or copper solid, right? Those are all elements. You're going to find 0 in the table. Just memorize that. It's easy, so you don't have to go looking for it and then find out, oh, yeah, it's 0. I remember now. It's an element. Now, if it's an ion, it's not 0, okay? So if you have Na+, that is not going to be 0. But if you have Na, which is sodium, which is an element, it's going to be 0. All right, let's just do a couple of examples here so you get an idea what's going on. So here first, I just want to do something silly. Write the chemical equation for the heat of formation of magnesium oxide. So first, you want to find out what the standard state is for magnesium. Magnesium is normally a solid at room temperature and room pressure, and oxygen is normally a gas at room temperature and room pressure. So you write out the chemical reaction magnesium plus oxygen yields MgO, all right? And we have all of the states in there. And then you want to balance the chemical reaction. But remember that since here in step 5, we want to divide all the coefficients by 2 because the heat of formation is defined for 1 mole of product. So in step 4, we have a balanced chemical equation that shows 2 moles of magnesium oxide. Divide everything by 2, and that is the chemical reaction that would describe the formation of 1 mole of product. And that's basically it, okay? Now here's Appendix G, and I do want to point out some features here. We're going to use this later on in the class, but we want to use the first column. The delta HF0 there is in units of kilojoules per mole, all right? Kilojoules per mole. You can see here how aluminium is an element, and it has a heat of formation of 0 because it's an element at standard state. And the other thing I want to point out is that you want to watch out for states, okay? Aluminum solid is 0, but aluminum gas is 324.4, okay? So when you're looking at a chemical reaction, it's critical to use the appropriate state. A balanced chemical reaction that's given to you is always going to have a letter next to it, aqueous or gas or liquid or something, to tell you what state we're talking about. So make sure you get the appropriate number from the table, all right? And that's all I wanted to show here. Now, some of the values are positive and some are negative. Please use this sign in your work, okay? So the way you calculate the heat of reaction, remember again, this is the change in enthalpy for a chemical reaction, but I just call it the heat of reaction. You're going to want to refer to Appendix G in the OpenStax chemistry textbook and use this formula. So write this formula down. The heat of reaction is equal to the sum of the N times the heat of formation of the reactants minus the sum of N times the heat of formation of the products. Now, what is N? N is the coefficient for each chemical in your balanced chemical reaction. It could be the reactant or it could be the product, okay? And the heat of formation, right, is the value you get from the table. And again, caution, caution, be sure to use the appropriate state, solid or liquid or gas or aqueous when you're doing these calculations. Here's example 568C. For our first step, you want to consult Appendix G in the OpenStax chemistry textbook and gather all the heats of formation, and we're going to write them down under all of the different reactants and products here, okay? So we get negative 824 for the iron 3 oxide. Hydrogen is an element, so it's 0. Iron is an element, so it's 0. Water is liquid, so make sure you use the liquid number, and I found that to be negative 285.83. Next, we want to write out our formula and begin working off of that, okay? And so it's really important to remember where the products are. In the formula, products come first. In the chemical reaction, products come last, all right? So watch out for that. The products are on the right side of this chemical equation. There's iron, which is 0. We can just ignore that. And we have 3 water molecules, okay? So this is where N is 3 because the coefficient of 3 there in front of the water means that we take 3 times the negative 285.83, okay? And then we have a subtraction symbol in the formula, all right? Don't forget that. It can reverse signs and do weird stuff, okay? And then we have to add up all the reactants. Remember, reactants are on the left side of the equation. Hydrogen is 0, so I'm just going to leave that out to simplify our discussion. And we have 1 mole of iron 3 oxide, so we enter that value in here, remembering to use the negative sign, okay? The one thing you have to worry about when you're doing heat of reaction calculations is to always watch your signs. On the right, we have a subtraction of a negative 824.2, so that gives us positive 824.2. So I'm going to go ahead and multiply the 3 also. So 3 times negative 285.83 gives us the negative 857 there, and now we have a plus there between those two numbers. And then all you have to do is go ahead and add up those two numbers, and on my calculator I get negative 33.3 kilojoules. And I just add units to the very end after I've done all my work, all right? And your units are always going to be kilojoules, all right? Now, we don't say kilojoules per mole because there's different molecules that we're talking about, and they have different coefficients, so it's always just going to be kilojoules, all right? The value negative means it's exothermic. Having no idea what this chemical reaction looks like, it's going to give off heat, all right? Let's do another one. So here we want to start again by using Appendix G to get all of the appropriate thermodynamic values. So here's an interesting chemical reaction. We have carbon disulfide in the gas phase reacting with chlorine gas in the gas phase to produce carbon tetrachloride in the gas phase and S2Cl2. I don't remember the name of that. I think it's disulfuryl chloride. You might look that up if you're interested in knowing that, okay? All right, so what we want to do is, again, just write down the numbers, and I'm writing them here on the board. Now, what you really want to watch out for is that when you look at the table, please look and do this yourself, you're going to find 2 different numbers, one for the gas and one for the liquid, and you want to use the gas numbers if you have gases involved in the balanced chemical equation, which we do in this case, all right? Next, we grab our formula, and here the coefficients are going to be very simple. There's 1 carbon disulfide, there's 1 carbon tetrachloride, and there's 1 S2Cl2, right? And the chlorine gas can be ignored because it's an element with a 0, okay? So we have 2 products, okay? We have 2 products to add those up. we have the carbon tetrachloride and the S2Cl2 molecule. And that's what the summation symbol helps us remember, that little sigma symbol, right? It means you add them up. And I like to use brackets around the products like this, and that keeps my signs from getting messed up, okay? But make sure to keep your signs separate from the operations, like minuses and pluses. So I like to use the parentheses. I kind of overdo it a little bit, all right? Now, there's only one reactant, and it's 116.9, right? But don't forget that we have a subtraction from the formula. And at this point, it's really easy to do all the work with the brackets. I like to do all the works in the brackets. Go back a page. I like to do all the work in the brackets first on the left for the products, and then I like to do all the work for the brackets on the right for the reactants, because sometimes you're adding up 2 or 3 chemicals and you have coefficients in there, and I like to do that all as a separate problem. And then once you get 2 numbers and you have the subtraction in the middle from the formula, then I just compute it and figure out what that is. This problem was pretty simple, so I just did it all in one step. And here we want to round the answer to the 10th place. I don't like this table from the textbook because some of the numbers are out to the 100th place, but we want to round this off to the 10th place. And of course, please put your units at the end of the number. The units here are always going to be kilojoules. That's the unit of energy here. And that, in a nutshell, is how you calculate the heats of reaction using the thermodynamic tables. The rest would just be more examples, and I think you've got an idea and it's been introduced to you. Thanks for watching. Please consider subscribing to my channel to support me, and have a great day, everybody.